into deeper and more important algorithms based on trees, you'll be like very good. What's good, you guys? In this video we will be talking all about trees, which is actually a very important topic in your data structures and algorithms. And in this video you will get the whole idea about tree, its types, so that when you will be diving into deeper and more important algorithms based on trees, you will be like very good. So if you are new to this channel, do consider subscribing to the channel. I'll be coming up with very beneficial and informational videos in future. So do consider subscribing and liking the video. So that's it. So let's get into the video, and you'll be seeing the screen next. Okay guys, so let's see what is a tree, right? So before we understand what is a tree, first let's understand what is a node, right? So we can just like understand node as a basic unit which contains datas, right? So like you can just consider that a data node is a kind of storage unit which can contains any kind of data, right? Like any number or string, anything, it can contain anything. So you can just understand that that is that, right? So now okay, so we are gonna see. Okay, so let's see what is a tree, simple tree now, right? So what is a simple tree? Okay, so yeah, I think the best way to understand tree is recursively, right? So we can, okay, so a tree has a root node, so there is always a starting node that is called root node, from which there are branches, and those are edges which get connected to different nodes. So the root node has zero or more child nodes, right? So it may have zero or more child nodes, and so thus recursively each child node may also have another child node, so it may go on or not, right? So before we see what is a tree, let's just see how a node is implemented in code. So this is what a node looks like. It has a data. Here we are taking integer as data. Yeah, integer as a data. You can take any kind of data. You can just store any kind of data in here. Then it has a left child and a right child. For them, this is the declaration, and here just for further convenience we take a constructor which we can call anytime we want to make a node, right? So when we just have to make a node, we have to just in the main of our program, we just have to call an object of this uh, node class, that is object is new node, right? Then we can just pass any value, and here we are, we have a new node formed. So this is kind of how it works, the class node. I just wanted to like explain, like node is an entity which contains data. For this video we just want to want to know that, right? So let's go further ahead, guys. So now let's see a basic representation of a simple tree, right? So not any kind of tree, just a simple tree. So this is what every tree has in common. So it has a root, right? Like we discussed earlier, it has a root that is a starting node, right? Then we have their children's, which may have or may not have their children's recursively. And also, if you're wondering what is a leaf node, so a leaf node is a node which does not have any children of its own, or basically it is the last node. The last nodes or the ending nodes, we can say that these are leaf nodes. So in this case, in this tree, this is a leaf node H, I, J, E, F, G. These all are leaf nodes, right? So now okay, so parent node, so any node which has its own children is a parent node. So in this case, this is a parent node, this is a parent node, this is a parent node. So any node which has its own children is a parent node, and the children's are the called the child nodes. These are the basic things, all right? Okay, so now let's see what is a binary tree, right? So as the name suggests, binary means two. So what it corresponds to is that every node in a binary tree has at most two nodes, right? It can't have more than two nodes. So it can have zero nodes, it can have one node, it can have two nodes, but never max than that. So if we see this tree here, right, so this tree is a binary tree. Why? So let's check out why, right? So every node here has maximum two nodes. So if you'll see, it has two nodes, this one has two nodes, everyone has two nodes. And so if we'll see the sixth and the seventh node, they have each have one no respective child nodes, right? So which satisfies our the rule of binary tree, that is we can have at max two nodes. So it has one node, so this whole tree, we can say that this is a perfect like binary tree. Okay, so now if we go to, so for just the sake of comparison, you can just understand like what is the difference between a general tree, simple tree, and a binary tree. I have uh, make this picture, right? So you can just compare. So why this is not a binary tree, why this is not a binary tree? Because if we see this node, the starting from the root node, we have already have four nodes, so that violates our rule, right? So this is not binary tree, right? So although all these have two nodes and this is one node, these all satisfy, but any one node, any one node in the tree just not qualifies with the rule, it is out of the league, right? So it is not a binary tree. Okay, so now let's go to the next tree. Okay, so guys, pay attention to it, because binary search trees are really important. And let's now see what a binary search tree actually is, right? So now let's see what is a binary search tree and how it is different from a normal binary tree, right? So as we know till now, that like a binary tree is a tree which has maximum two child of every node of it, right? So binary that same property also applies to the binary search tree, because it's also a binary tree, but the thing that differentiates it from the binary tree is that these two conditions are what differentiate it. So let's see what the conditions are. So to be a binary tree, to be a binary search tree, it should satisfy these two conditions. So let's see what is the first condition, right? So the left subtree of a node contains only the node with keys lesser than the node's key, right? So that means that every node's left node should always be smaller than the that parent node. For example, if we take this example, this is a binary search tree and this is a binary tree, right? So if you take this binary search tree example, we can see that every left subtree, every left subtree is less than its parent node. So that is a condition of binary subtree and it satisfies it, right? So, and the second condition is that the right subtree of the node contains only node with keys greater than the node's key. That means the right node of the parent node should always be greater than the parent node. So see, every you can evaluate every node of this graph based on this property, and you'll always get the get that it satisfied it. So let's see, it is the parent node, its left node is less than it, so it's right here. It is the right node, it is greater than the parent node, it is right here. So now let's consider this tree, this subtree. Here it is the left one is less than 3, 6 is greater than 3. So everywhere you see it satisfied it, so it is a binary search tree, right? So what you like, so at last what you'll find is that all the larger elements you'll find it on the right side, and all the smaller elements of like comparing to the parent node, you will find it on the left side. So this is a property of binary search tree. Okay, now let's see what is wrong with this graph, right? What is wrong with this graph, that it is not a binary search tree and just a binary tree, right? So if we see, as you know the conditions, you just have to remember this, like the parent node should always be greater than the, sorry, in more simplified form, you just have to know that left child of a parent should always be less than it, and the right child of a parent should always be greater than it. So that's how a binary search tree is formed, right? So if we see this graph and just evaluate it where it goes wrong, so we find that in the first case only it does not satisfy the conditions. Like we know that left child should be always be less than the parent node, but here it is greater than, so here we go wrong. And so any other just one mistake we find that it does not satisfy it, so it is not a binary search tree, just a binary tree. Why? Because at most every node have two childs. That is the condition of just a binary tree. But here if we find that every left child is smaller than the parent and every right child is greater than the parent, that makes binary search tree, and that makes this not a binary search tree. So I think now we have completely understood what is a BST or binary search tree. Now let's move on. Okay, so now all the remaining trees are pretty easy to understand, so just stick with me, right? So we have here a complete binary tree. So what is a complete binary tree, right? So before I tell you this, you need to understand that a tree is filled from left to right, not right to left. So first 10, then 5 and 20, then 3, 7 and 30, right? So from left to right. All right, so what is a complete binary tree? A complete binary tree is a tree in which every level is fully filled except maybe the last level. So what that means is a complete binary tree, all the levels are fully filled except we can spare the last level. So this here is an example of binary complete binary tree, and this is not. Let's see why. So if we start filling in 10, okay, we filled in, right? 5 and 10, it is also, this level is filled in. Fourth level, third level, which is the last level, is filled here, filled here, filled here, but not, this one is not filled. But that's okay because it's mentioned that maybe the last level can be spared, right? So if we see, but if we see that this diagram, this tree, so here 10 is filled, then 5 is filled, okay, we are going right. 20 is filled, right. 3 is filled, 7 is filled, right. But here it is the last level, but there is something missing here, right? And then we have also filled 30, but if we haven't filled 30, then it would be regarded, it would be considered complete binary tree. But as we filled 30, so here something is missing, right? So this is not a complete binary tree. So I guess you understood what is a complete binary tree. Now let's move on to the next, right? So it is pretty easy, right? So that is what I was talking about next. So that was what I'm talking about. These are trees are pretty easy to understand, but the important most is the binary search tree. That is you have to understand pretty like strongly. These all trees are not that important, right? Okay, so what is a full binary tree now? Okay, a full binary tree is a tree in which every node has either 0 or 2 children, right? So in this case, this here is an example of a full binary tree and this is not. Let's see why. All right, so if you see every, so our condition is that every node has either 0 or 2 children. So here every it has 2 children. This has 0 children, this has 2 children, this has 2 children. So it is pretty simple. Okay, and now see, let's see why this is does not or it is not of a full binary tree. Because okay, 10 satisfies the condition, 20 satisfies the condition, 3 satisfies the condition, but 5 has just one node which is which does not satisfy the our condition, right? So here it disqualifies for a full binary tree. So it's pretty simple, right? So that's that. And now let's go to our last tree. All right, let's see what is a perfect binary tree. All right, so perfect binary tree is like is very perfect because it is a combination of both full and complete tree. So as you know, what is a full binary tree? A full binary tree is a tree which just which has two, which if it has node, it is two nodes, right? not one, not anything, just 2 nodes or 0 nodes. And a complete binary tree, as we know, is a tree which has like every level is filled with all the, like, everything is filled with all the nodes, right? So so this makes it a perfect binary tree. So this is an example of perfect binary tree. Everyone has 2 nodes. Full node is satisfied. Full node is satisfied, and complete, every level is filled, completely satisfied, thus making it a perfect binary tree, right? So interesting fact about this tree is that it must always have 2 to the power k minus 1 nodes, where k being the number of levels in the tree. So let's see how in this graph we have 4 levels, right? 1, 2, 3, 4. So in this graph we have 4 levels. K is equal to 4. So now we have the formula 2 to the power k minus 1. Let's put it. 2 to the power 4 is how much? 16, right? 16 minus 1 is 15. Now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So this is that, right? So I think it's enough for this video. Now you have understood all kinds of trees that are present in this whole world. Not literally tree, but yeah, right? So that's it for the video. Hope you understood and took something away with you from this video. So thanks for watching, and do subscribe to the channel and like the video, and I'll see you in the next video, right? So till then, stay safe, stay happy, and be future driven.